Today, we're very happy to have Cari Cesarotti, and she's going to tell us about No Stone Unturned, a comprehensive approach to new physics research at colliders.
So thanks, Sophie. It's great to be here. Today I'll be talking about how we can sort of take a more comprehensive approach to looking for new physics with colliders. So before I get started, I'm giving this talk as a theorist, but of course I'll be remarking a lot about the experimental program. But I want to remind us all about how important it is that these two things evolve as a conversation. And that's important, of course, for the scientific method in general, but in particle physics, I think that that is a particularly true statement. So a really nice example about how theory and experiment work together is the discovery of the JSI, which just enjoyed its 50-year anniversary this past year. So the story kind of begins with the Jim mechanism back in the 70s, which was, of course, the fourth quark was posited as a solution to explain why flavor changing neutral currents were so small. There needed to be a cancellation. And so this quark was suggested. Then a few years later, when we found this unexpected resonance, we were able to understand very quickly what exactly we were seeing. And once this resonance was detected, then we could go on and make further theoretical computations about what other particles of these quarkonia states should be showing up and what their masses were. So this is a nice example, of course, of how things happened 50 years ago. So how can we take this logic and pay it forward to understanding more about particle physics? Well, the current state of affairs of colliders and experiments more generally, especially in this country, were kind of set by the consequences of P5, which was this, if you weren't connected to it, I envy you, but it was this interesting bureaucratic process about how we recommend Congress to spend money in the future. So in the US, at least, we have prioritized upgrading our current collider, the LHC, thinking about a future Higgs factory to do precision Higgs measurements, and a really interesting new technology possibility called a muon collider to be considered in this scheme of experiments. But really what I'll talk about today is sort of how we can use all of these different experimental intuitions and bridge that with theory in order to maximize the discovery potential, especially with beyond the standard model physics. So before we get too far into beyond the standard model physics, let's remind ourselves what we do know about the standard model, which is, of course, the catalog of all known fundamental particles and their forces. And so the purpose of particle physics is, of course, to understand the most fundamental degrees of freedom and how they interact. And the way that we have made progress in understanding this, I think can be nicely summarized as a function of the collider energies with which we have been able to achieve. So as we have gone to higher energies in colliders, we've understood a lot more deeper truths about what's going on in the standard model. So beginning with colliders, we've understood that there were these higher generation particles starting to show up. So we have this idea of flavor symmetry coming online. At even higher energies, we were able to understand the gauge structure of the standard model and to uncover and show some proof of this electroweak gauge symmetry that was occurring. And then most recently, we have the Higgs mechanism, which we think is consistent with the explanation of masses of particles. So as we've got more energy, more fundamental properties of the standard model have been understood. But of course, there are still a lot of open questions that we have towards the standard model that we know pertain to at least things that we've already discovered. So I think some of the biggest questions that we have relate to the Higgs boson. You might, of course, think that because we found it and we've measured its mass, we know everything we could, but in fact, there's huge error bars onto what we understand about the mechanism of the Higgs boson. So at the LHC, we've only really been able to measure one parameter of this potential quite well, and the rest is still pretty unconstrained. So this wine bottle potential is not the only story. All of these potentials are still consistent with just the thing that we've measured at the LHC. So we really need more energy to be able to collapse this and understand the true pattern of electroweak symmetry breaking. Additionally, even though we know that flavor exists, the origin of this hierarchy of flavor is something that we still have yet to understand and is kind of a surprising fact that's not motivated by much. We also have some problems like the strong CP, which we expect to be perhaps not quite as small as we're seeing it. And we can have these precision measurements like the electron EDM that can give us kind of bounds about where we expect the standard model to be, but we're still orders of magnitude away from what a prediction might be. And this is all still consistent with potentially new physics showing up even in the tens or 100 TeV range. So the problem with that is even a bigger pathology too, is that not only are there questions about the degrees of freedom of the standard model, but there are questions that cannot be resolved with these degrees of freedom at all. And so these are an important question to answer as well. So of course, some of these questions are dark matter. Does dark matter have a particle content, or is it something else completely? What is the origin of this baryon-antibaryon asymmetry? Why is the universe made of matter and not antimatter? And of course, as we do more and more precision measurements, anomalies tend to crop up. So an important example recently was a W anomaly, which of course, the mass of the W seemed to be different than the standard model prediction, but that's been resolved a bit by the most recent CMS measurement. But if it's still pulling a little bit high, we can have new physics showing up in the TeV range that could explain this mass correction. So there are still problems that we face that suggest, along with the arbitrariness of the standard model, that we have far from completed the picture as to what these particles are. But the problem that we face in particle physics is something kind of pathological in how we formulate our questions, is that we don't really have a singular guiding theory that should be telling us where to look for the solutions to these new physics problems. So instead of going after a single theory, what I propose that we can do to make progress in particle physics is instead embrace the era of exploration. And so that is, instead of looking under lampposts that have been established for new physics, intentionally and with motivation, install new lampposts that can give us a more holistic picture, and with empirical evidence, we can again reformulate our theories to understand more deeply what is going on with nature. So the experiments that we have that are sort of the most general purpose are these collider experiments. And so we can do broad searches for new phenomena, both new to standard model, but new particles as well. And from there, we can take those empirical hints and have more motivated, targeted theories that we can chase after. So the point is that these searches should be robust in the sense that they're robust to specific parameters of the theories with which we are probing, but not random. The point is not that we're trying to fill a volume with measure 0 points, is that we're trying to go after things sort of more comprehensively and try to identify behaviors of new physics with this collection of large experimental searches.
Is that a neutrino collider that's given there? Or?
Neutrino experiments?
Yeah.
No, we shouldn't collide neutrinos. That's very hard to get much. No, so the point of neutrino experiments is that they often require very high intensity beams. And when you produce neutrinos, you're producing a whole bunch of other stuff as well. So you produce neutrinos with a lot of times things that decay and give you interesting flavor measurements. So this is just a statement that you have a high intensity but low energy beam. Yeah, so what I'll be talking about for the rest of the talk today, and great, please shout out questions as you have them, I love it. The idea is that we should be developing model agnostic tools and search strategies in the context of current, future, and auxiliary collider experiments. So the outline of the rest of my talk will be as follows. First, of course, we want to think about how we can maximize the discovery of the existing tool that we have, the LHC. Then I want to talk about what interesting novel opportunities we will have with future colliders as we progress on that avenue. And sort of something in the middle in terms of what timelines we should expect to achieve these things on is how can we reuse or repurpose experiments to do new things with old infrastructure. And basically, this is, again, a big cartoon, but you should think about this as sort of how we'll be mapping out the different areas of theory space. So let's start with what we already have and how we can do these model agnostic and versatile search strategies. All right, so I know not everyone in here thinks about collider phenomenology very much, so we're going to start very broad. And that is reminding you what is the current collider that we have. So probably everyone knows we have the Large Hadron Collider, the LHC at CERN. It exists on the border of France and Switzerland. And there are two general purpose experiments called ATLAS and CMS that exist on this accelerator ring. So the energies that we look at are 14 TeV nominally is what we're looking at, but we're colliding protons, which of course are not fundamental particles. And so the energies that we're able to probe suffer the suppression from the PDFs because the partons are the things colliding and not the actual proton themselves. So because of the energy distribution of the actual partons inside the proton, we're really seeing collisions at much closer to maximally 3 TeV rather than that 14 number. So we're only kind of barely going above the electroweak scale. Of course, the data that we've been able to take will be increasing in time, and we've already collected quite a bit. So we've collected, by the end of run 3, will be about 300 inverse femtobarns. For those of you who don't think in cross sections very often, that's equivalent to tens of petabytes per year of data is stored from these collisions. And we've seen about 10 million Higgs events at the LHC. We expect this to go up quite a bit with an upgrade that is planned and approved called the high luminosity or HL LHC, which will increase these collisions and give us roughly 10 times the data to come. And this will happen in sort of the 2030s, ending in maybe early 2040s. But of course, with more data comes more problems, because we just simply do not have the technology to read out all of these collisions and store all of this data. So there's a process that we call triggering, which is the pre-selection of what events are even worth reading out to save to analyze. And when we go into this HL-LHC era, we'll have to reduce by a factor of 10 million the events that we actually produce and the events that we can study. So when you're trying to do something without knowing what you're doing, and you have to cut out 10 million times the events that you're looking at, it's very easy to miss a needle in the haystack. So all of us that kind of think, oh, the experimentalists definitely have done everything they could, this number should make you rethink that conclusion. Moreover, there's kind of a fundamental problem that we have about how do you actually map an underlying theory towards the kind of collider events that you see, and that is a very non-trivial mapping to do. So if you personally can look at this Lagrangian and then see how that shows up here, you might be a machine, I don't know what to tell you. But the point is that as theorists, we need to create ways to actually understand how the bare parameters of a Lagrangian that we write down actually manifest in collider events. And so what we do often is think about observables, which are functions of the actually observable quantities that we would see at colliders that have a straightforward interpretation of what's going on in your underlying theory. And even then we have the problem that it's not like we can exhaustively search for new physics, because theory space is infinite. We can always perturb around some kind of theory, and the collider signatures with which different theories can generate can also be degenerate. So this is a very far from completely searchable problem. So what we should be thinking about as theorists that work on this is that theory is the sieve for finding hints of new physics in this ridiculously large data haystack. So there are a couple of ways that we can sort of design this sieve to tease out possible signatures of new physics, or at the very least for standard model events as well. And we want to again do so in ways that capture broad categories of new physics events rather than going after a singular model. So one thing that we can do is just make precision measurements. Precision measurements, even though they measure something in the standard model very precisely, are also secretly new physics measurements, because basically if we disagree, there has to be new phenomena that's contributing to this disagreement. So it doesn't tell you what the disagreement is, but it tells you it's there, which at least gives you something to go off of. So again, there's some example that we could do with the global fit of the electroweak parameters after studying the mass of the W. Something a little bit more hands-on with the data itself is using open data, or data that's experimental grade, to actually have theorists sort of test drive different analysis strategies. Such an experimentalist can come in and do much more of the dirty work with the actual unfolding and things like that later on. But we were the first group to actually just demonstrate that you can do some kind of new physics search with data as a group of theorists, which happened much faster than it might in the global collaboration framework. But the thing I'll talk about mostly today is how we can just develop new observables. So again, these new mappings between sort of theoretical categories of new physics and how they would represent in the colliders themselves. So again, the point of these observables is a translation. And we want to understand how we can sort of take what we know in the theory and see what global characteristics would show up in the radiation pattern of the particles coming out of the collision. So again, you could think about this in terms of precision observables. So this is a very good tool to use when the theory is quite well established. So this makes a lot of sense for standard model tools because, again, we know the standard model is quite high precision, and you can take very well parameters that are measured in the Lagrangian and then use that to project how well other parameters should be measured as well. But that's not really what we're going for with this search of new physics, is we want something that gives you a bit more general features of a theory. So instead, what I propose is that if we want to take the most generic new physics signature, is try to lump categories of new physics that just look inherently non-standard model. So what we're trying to do with this line of my research is we want to maximize the contrast specifically to QCD, because of course QCD is what we're primarily seeing when you collide protons at the LHC. So if we want to go in this orthogonal direction to what we see in QCD, perhaps the first thing that we should do is understand QCD and then go in a different way. So let me remind you what QCD observables have been quite lucrative in understanding new physics or standard model in the past. So we all know that QCD is strongly coupled at low energies, which gives us a phenomenon of hadronization. But at high energies, because of this logarithmic scaling of the beta function, is we actually see very different phenomena. And instead, QCD at the energies of colliders is characterized by these soft and collinear splittings. So you can see that if you just have this gluon emission that's got some fraction of the quark it's coming off of, is the enhancement of the diagram that emits a gluon is going to be proportional to 1 over the fraction energy carried away and the angle of emission. So there's a strong enhancement of having these soft collinear gluons addressing these states. So what kind of experimental signature that gives us is this jet, this very collimated spray of energy that eventually, as you lose more and more energy in the shower, has to hadronize in the end. But to zero quarter, what the parton picture of this would look like is if you have 2 particles come in, you have 2 particles come out, and then the fancier states are, of course, stressed with all of this QCD stuff happening in between. So one of the ways that we can characterize this very messy hadronization procedure without being too specific about the individual points of hadronization is by just looking at the state at the very end, the global behavior. So what we can do is look at the radiation pattern, which is just in layman's terms, basically the 4 momenta that you can detect at the collider itself, and then try to understand what is going on from this. So one of these excellent observables that have worked historically is thrust, which is again used to sort of measure how much soft and collinear emissions happened or to what degree that was violated early on in the shower. So thrust is a really simple observable to explain. Basically what it's doing is it's maximizing this axis that we call n hat, which is known as the thrust axis. And the idea is that primarily, again, the zeroth order picture should be happening. And that would be the thrust axis. So all these other emissions are happening kind of collimated along this. And so it's telling you basically how far particles are coming off of this particular axis. And it was used even to understand alpha strong in the early days as a way of measuring basically these finite angle emissions. So what we're going after here is quantifying how similar your collider process looks to what you would expect from high energy QCD. And this was very useful again in the past for understanding things that sort of sit in this regime of these topologies. So if we want to think about something just complete, then we can have these sort of 2 extremal events where we have this either dipole configuration where no radiation came off at all, or the absolute opposite end of the spectrum where you have a very isotropic looking radiation pattern. So QCD will sit much closer to this end, and thrust was very good at understanding these events. But there are other signatures that are interesting to go after, especially with either rare or new physics processes. So you can start to push further to this somewhat isotropic looking radiation pattern if you have either multi-jet events or things with a lot of particles in the final state. You can think about it just from kinematics. If there's a lot of kinematics or a lot of objects, none of them can have a particularly strong boost. So just in the large limits of particles in your event is that you have something that kind of approximates a uniform distribution. But you can also have just a new physics theory that should start to approximate an isotropic event. And that is partially, yeah, if you were to have a new theory that's strongly coupled, so meaning it has a large Tooft coupling over a large enough window such that a shower can progress to have this sort of spherical distribution. I know this story must look similar to Juan because he was one of the authors on it. So yeah, I'll just say the Hoffman and Polchinski-Strassler demonstrate that this is true. So the reason that we can't really search for these kinds of events with thrust is because thrust tends to saturate quite early. So it's not really sensitive to anything beyond sort of these small emissions away from the dipole. And so everything that looks just clearly not dipole looks roughly equally not dipole. And it can't really tell you sensitivity between these different kinds of perturbations in that regime. So what we want to do is design an observable that is sensitive to this region to act as a complement to what we can learn from thrust. And so we come up with this observable that is called event isotropy that is meant to act in this region instead. So another interesting theory question that you can ask and things that we should be working on is how do you even generate events that are in this regime? You start to lose your handle of perturbation theory. Simulations do really poorly with high multiplicity events. And so we came up with a sort of 5D simplified model that can tackle this problem, but I won't talk about it today. So if you want to ask about it, please come up to me after. Okay, so let me describe to you what this observable is doing. And ultimately what we're trying to do is we're trying to quantify a distance between a radiation pattern that you would see in an experiment and an isotropic reference event. So the isotropic reference event is sort of what you assume your theory would give you, and you want to see how far away the collider event will be. So these simulations, I think, kind of help visualize. But the idea of what we're doing is we're trying to quantify the least amount of work and work almost in a technical sense because it's going to be a force over a distance kind of thing. And we rearrange one set into another. So the two sets are going to be the sets of four momenta, where one set is the collider event and the other is the reference event. So we need some sort of mathematical definition to make this a consistent quantity. And so we use the energy mover's distance or the earth mover's distance, but made for particle physics. This is a very overloaded acronym these days. But the idea of what we're calculating is just like thrust, it's also going to be a minimization, but you're minimizing over this transport map that tells you how you move the energy of particle I in your first set to particle J in your second set. And then you weight the energy moved by the distance with which you have to move it. So it's really this idea of moving some weight over a distance kind of.
Distance in what space and what?
Yeah, great question. So the distance that you can define, here we define it to actually be like an angular distance that you move around. So the idea is truly the distribution in the detector. But some follow-up work have been done by my collaborators that talk about how you can sort of generalize this to moving it in theory space even too. So it's a very robust definition, and here I'm applying it to.
Okay, so it's some kind of
Sectors.
distance.
Yeah.
And once again, the two sets, you're moving one set of data to another. What are the two sets?
Yeah, so the two sets is you're trying to compare a collider event like this to a reference event like this.
Where does the reference event come from?
The reference event is supposed to be the stand-in for what kind of geometry you would expect from a theory. So the point is that
There's a theory bias.
there's a theory bias, yeah. And the theory bias that I was choosing here is that thrust kind of does a very similar calculation to this, but for the two particle case. And so I wanted to explore the complement, which would be the isotropic case. So right now we're just trying to establish two axes in this kind of observable space. Yeah, great questions. Good, so then these are just mathematical definitions to make it consistent, but yeah, as we talked about, you're weighting just energy moved by distance. That makes sense for the problem you're answering.
Do you have that minimization problem? Is it complicated or?
It can be. If you have a symmetry like we have with the isotropic, it gets much easier. But generically, the minimization scales as n cubed log n. So if you don't have an underlying symmetry, it can be a very computationally expensive thing to do. There are some talks of machine learning and projecting it to lower dimensions that can speed up this process, though. Okay. So to show that this observable is actually useful and not just redundant with other things we already know, we have to answer some very baseline checks, but ultimately we show that this is useful for BSM as an additional handle to other kinds of observables that we've used. So the zeroth order thing that I have to prove to you is that this does in fact map to a complementary dynamic range to thrust, otherwise there's no utility for this observable. So what I'll show you here is actually results from a short-term association I did with the Atlas experiment. So they invited me as a theorist to help them analyze data, so that this is all actually experimental grade Monte Carlo and data. So kind of as close to the real thing as you can see, at least in Monte Carlo, and then I'll show you data as well. So what we're looking at here is sort of minimum bias QCD events, where we separate out the different events into the number of jets that you find after clustering. And then we map those distributions in both event isotropy and in thrust. So of course this is Monte Carlo, because otherwise you don't have a truth level of how many jets should be in the event. But it's not so interesting if you look at the overall distributions, but if you look at the distributions normalized by the total number of events in that bin, you see that the different areas of these distributions are occupied by very different underlying physics samples. So in thrust, basically it does its job that I said it does really well, is that it can say this is two particles over here, or two jets, this is three jets over here, but everything in the middle is kind of a mess. But with event isotropies, we do have that additional sensitivity to basically tell you where the number of jets is maximized for all these different samples. So you have a much stronger idea as to what is likely being populated in that regime for event isotropy rather than thrust. So how can we use this information? Well, let's go and look at what we actually get from data. And so what we find is that this is a way of identifying poorly modeled dynamics at worst and potentially new physics at best. But I won't claim that today, so don't quote me on that. So if we look at the same distribution, but now in data, of course, we can't separate into truth level number of jets that we see. But again, here we have data in event isotropy, and at the bottom, we're comparing the ratio of the simulation results to data. And you see in particular at some points, the simulation and data really start to disagree. And we can understand exactly what is happening there, not because of what's going on in thrust, but if we look over at event isotropy, we see that basically where experiments disagrees with simulation happens when we get beyond 3 jets in our event. So what this is telling us is that our simulations are not doing a good job at modeling high multiplicity QCD events. And so it's rare to see this in data, but it is still important, especially as we have more signatures that demand high control over large multiplicity QCD backgrounds. So this is telling us how we can improve our simulations. It could be telling us that there's new dynamics, but that's probably a very charitable interpretation. But the point is that as we have more and more handles to control poorly modeled QCD, we can improve the sensitivity of our new searches in that regime. Yeah.
Alright, sorry, so when you say that simulation is not doing a good job of modeling these multi-jet events,
Mhm.
you mean that like the sample generation level at like density, or do you mean, is this more a statement about like the reconstruction algorithms?
Yeah, so this is, yeah, it's what I suspect is going on here is it's a failure of the matching algorithms. So basically when you do this, right, there's some part of the diagram that you generate just by doing perturbation theory and you have more and more emissions. There's another part that's just doing this parton shower model. But of course, these two things overlap at some point and you generate the same diagram. So exactly how you match what's generated at like Feynman diagram level versus at the shower level is a very tricky process. So what we're learning here is that's probably not being done well. And you see that especially because the different simulations diverge in different ways. So at the very least, you can take this observable and use it as a filter to say, if your event is too far from the ratio, throw it out. But also ideally, it could also tell us what kinds of space in Monte Carlo space are we getting these sort of pathological disagreements. Yeah.
Is this new variable event isotropy?
Yeah.
Is it infrared safe?
Yes, it is by construction infrared safe, because if you take, it's IRC safe, right, is that if you take the distance or the energy to 0, is then that weighting disappears. Yeah, so by construction, yeah, great point though. Because that is the pathology that sphericity had, right? Sphericity was not IRC safe. All right, so there's a lot of other ideas that I think we can do forward. So I'll just go through these quickly, is that, you know, as mentioned before, you can change what sort of distances you use. So if you don't want to be worried about small distances, if you're using big objects like jets, you can change it so that, you know, you focus less on the near stuff and weight very heavily the far stuff. Or you can do the opposite too. So depending on what you want to study in your event, you can change this distance and get a different kind of precision. We also brought up this point about, you know, what kind of theory bias do you introduce as the reference events? You can think about any sort of other geometry. If you think about, you know, doing a quark-like study, perhaps a plane would be an interesting geometry to compare to. So that's something I want to look into. And then just the idea of how do you use this to really do more advanced discrimination studies. I found that if you just plot this against the particle number, is that you can have this really powerful discrimination. But again, machines are much better at this process than I am. So I suspect machine learning could tell us even more how to get discrimination, especially in tricky events like TT bar. So I think there's a lot more that you can do with this kind of class of observables. So I don't want to spend too much longer talking about current colliders, but of course there's a lot of other things that you can do, and I don't mean to present this as an exhaustive search. But again, we should be thinking about how to robustly capture new physics rather than just randomly trying new models. So the punchline of all this is that, you know, as we do these generic searches, what is likely to come up is that we can have hints of new physics, but without a dedicated search, it's very unlikely we can say anything definitive about what the new model actually is. So if we were to find hints, we will likely need at least new data, but also probably higher energy too. So that leads me to why this next part of the talk is also important to think about right now, is that what can we do and what will we need to do with future colliders. And in particular, I'm interested in the energy frontier, so we'll talk about an exciting opportunity there with muon colliders. So again, not to get too dragged down in the politics of it all, but now is the time that big institutions are deciding what the priorities of the field should be. And so because these decisions are happening both in the US and in Europe, there's an urgent need for theoretical work to inform these important decisions, because this is a multi-decade process that starts basically already. So just to give you some examples about how theorists can weigh into this process meaningfully, is that we need to understand what redundancies in the physics case exists for different machines, but also more importantly, perhaps, what measurements can only be done at specific machines and what physics are we losing if we build one over the other. I think something that's also very important is how can we be flexible in the design choice, because physics goals tend to move around, and we even see that and arguably suffer from it with the current stages of the LHC and its run schedule. So a flexible design is important. And then something that perhaps we don't think about, again, assuming that detectors are perfect machines that give us everything we want to know, is are there any critical experimental features that we need to make benchmark measurements? For example, if you want to discover a WIMP, you need tracking that's basically 10 times better than what we've already been able to do. So if we hadn't done this study, we wouldn't know that that was so crucial. But these are all the ways in which theorists need to be informing this process today and not in 30 years when we start to get data coming out. So let's talk about the fun stuff actually, which is the physics. And when we think about collider experiments, basically there's been two avenues with which we make progress in understanding the model. And that is either with precision or with discovery machines. So precision machines tend to focus on low energy areas where we can produce a ton of data, such that if we see a slight deviation in the data in the standard model, is that we can at least be sensitive and know that there's something causing this disagreement. So historically, we've been able to achieve the precision frontier with E+ E- machines. Electrons are fundamental and very clean, so we can do quite a bit there. But of course, this just gives us hints that there's some new physics in the UV generating these low energy effects. On the other hand, we can also think about discovery machines, which you just hit something with an energy hammer and see what comes out, and you can produce these new degrees of freedom on shell, and you can really understand the origin of what effects you might be seeing at low energy. So the particles that we know how to accelerate to high energies are hadrons, and that's what we do at the LHC. But currently, there's a very exciting third option that we might have, which incorporates elements of both precision and discovery, as you can have fundamental particles accelerated to extremely high energies. And I know you've had a talk on this recently, but that machine would be a potential muon collider. So I want to give you sort of a broad overview about sort of what kind of physics programs these machines will go after. If you want to learn more about muon collider, we have some nice community documents that flesh out the story a bit more. But I'll be comparing proton machines, mu+, mu-, which is what we mean by muon colliders, and E+ E- both in a circular and linear configuration. So again, the problem that I've already pointed out with proton machines is that you're colliding composite particles, and you need to accelerate your particles to much higher energies than you actually get to probe in the center of mass frame. So there was a nice community document a couple of years ago called the Muon Smasher's Guide, which basically shows that for comparable cross sections, you need to have roughly an order of magnitude energy more at a proton machine than at a muon collider. So 14 TeV muon collider is roughly the same energy as a 100 TeV proton machine. So you might argue that, okay, electrons also are fundamental particles, and so we can achieve higher energy with them and they seem much easier to use, but they suffer a very different pathology, which is that they're too light. So you can understand this with just E and M that we all learned in college, which is that an accelerating particle tends to radiate power. And the radiation loss is going to be proportional of gamma to the fourth, which is the energy over the mass to the fourth. So if you were to take the same machines and try to accelerate protons versus electrons to the same energy, is that your muons and electrons, your muons would lose a factor of 1 billion less energy. So clearly we can't have anything remotely comparable for these two machines. And generally what we talk about for E+, E- is that we want to do kind of at most hundreds of GeV, and linear colliders can even push that number a bit further, but still not arbitrarily far. So if we really want to go to the 10 TeV frontier, we do that with a 10 TeV muon collider or a 100 TeV proton-proton machine. The kinds of physics that these machines are primarily designed to study, of course, we have these really high quality QCD events that happen at PP machines. Muon colliders really study high energy electroweak phenomena, which again is sort of pivotal to understanding that Higgs sector that we don't quite know the full origin of. And E plus E minus go after the precision hints of what's going on with the Higgs by just producing a lot of Higgs in what is kind of canonically known as a Higgs factory, which is honestly a bit of a vacuous statement. You just produce at least 1 million Higgs. So all of these machines have various pros. For a proton-proton machine, again, we can go to the high energies and we know how to build it because we have built it. And basically the process is straightforward, just takes a while. For electron machines, again, we know how to do it and we can do this precision. And ideally, we would build these electron machines with the intent to upgrade them to either a much higher energy linear collider or ideally to this really high energy proton-proton machine as well. So currently the state of affairs is that CERN is very pro low energy electron machine in order to upgrade it to this high energy proton-proton machine, but that comes, yeah, Edward.
How much more expensive is that than if you just were making the Higgs factory?
If you add E plus E minus to PP,
No. If you just were doing the E plus E minus circular machine.
Yeah.
It wouldn't have to have such a big tunnel.
that's true. Well, okay, so if you wanted to have the amounts of statistics they had for the power consumption that they want to do is you still need the big tunnel. But if you did it at a linear collider, you don't need the big tunnel and you can do it with 8 kilometers instead, and probably closer to 5 billion than 15 billion. But truly, what is 10 billion in this world these days? I don't know what eggs cost anymore.
We won't record that remark.
Someone used to say it, maybe they should hear it. Okay, so, yeah, but, right, money is of course a form of trivial matter in this whole thing. And of course, yeah, the benefit with the muon collider is that you don't have to go through this one stage and the other, you just get both right away when you have the high energy and precision frontiers. But of course, there are also a lot of cons that come with these statements as well. So as Edward has pointed out, is that these kind of things for the proton-proton machine will have to happen in the very far future. They will be expensive and they will be somewhat new technology just in terms of the magnets that we'll need to fit it and the length that we think we can do it. Muons suffer perhaps a more important pathology, which is that we just haven't shown that this is a possible technology yet. So the next step in muon collider journey is not to start digging a tunnel for a muon collider, but rather to invest in the research and development to ensure that we can actually do this whole process. And all of this is basically because muons decay and it's hard to make bunches of muons. For E plus E minus, again, of course, we know how to do this. It can be a relatively cheap process. But if you want it to be able to go to the high energy, you need the giant tunnel or something to that effect. And the funding is uncertain, and we can't underemphasize how important this matter is. So if we put all of our eggs in one basket and then just the funding falls through, that could be the death of particle physics. So I think that really you shouldn't have in your mind that one option is the correct option we are definitely going after, but rather we should keep our strategies open. And especially because this is a cliff. And if we just build 100 TeV proton collider, that's it. That's all we got. So we better find the whole answer to the universe. But if we invest in a muon collider, is that we can potentially push that number at least by another factor of 10. So all of these technologies are, I think, still important to consider as very viable options.
When you say funding uncertain, do you mean in the US?
I mean, everywhere.
Even if you said CERN wants to do this, or?
So CERN's funding model is very interesting. They are looking increasingly into private donors for funding, because this would be a net in 2025 dollars, $30 billion endeavor. And asking the countries that signed the treaty to contribute to CERN to just, cough up an extra $10 billion, in particular Germany, in the next several decades is something that perhaps they might not feel like they can do. So there is pushback even within the member states.
You haven't mentioned China.
So that's a very interesting point too, is that China has given us a lot of signals that they are interested in doing something very similar. China also has an idea of doing an E plus E minus machine to upgrade to proton-proton. It's called the CEPC, upgraded to the SPPC if you want to look it up. I have gotten so many mixed messages that I truly have no idea what the status of that endeavor would be. I think it would, however, be an amazing catalyst to get the US to kind of push and do something cool. So quite frankly, I'm a bit pro CEPC if that just lights the fire and gets things started. But yeah, the take home is this is a mess. If anyone tells you with confidence that they know it's gonna happen, they're lying to you or they're delusional or both. So we should really be thinking about all of these possible options. Great, okay. So I'm gonna focus a bit more on muon collider because I presume that we're more familiar with E plus, E minus, or PP machines, given that, again, they've already existed. And I'll sort of talk about sort of the two generic broad physics programs that we can do with these machines. So one category, these are sort of the guaranteed deliverables of this machine that we tell people that will definitely be measured. And that is the electroweak sector. So Higgs and electroweak measurements we can definitely do, and we can really collapse this potential and understand the pattern of electroweak symmetry breaking down to something very specific by the measurements of the trilinear and quartic couplings of the Higgs. So we produce the Higgs in a very different process than at the LHC. Instead, we do this process called vector boson fusion, where you're fusing primarily W's, but also sometimes Z's to produce a Higgs, which can then, of course, branch into 2 or 3 Higgs as well. So at a 10 TeV muon collider, we'll produce 10 million Higgs bosons, which will have a comparable sensitivity to what we would do at a E plus E minus Higgs factory. On the other side, where I spend much more time thinking about, is we also have different channels of looking at beyond the standard model production of new physics. So some different categories that we have are just new physics pair production, which leverages the high energies that you will have at this machine. You can think about models that would be particularly enhanced at a muon collider and things that couple to sort of these heavy flavor generations. So if you couple more strongly to the later generations, just like the Yukawa would, that would be enhanced here. And you can also play the game of the effective field theory is that energy is also secretly precision as long as you think about doing operators instead of just measuring on-shell effects. But I'll just focus on sort of this category and I'll show you a couple of models that kind of represents the power that we would have looking at muon colliders, but aren't supposed to be taken as, you know, definitive things that we need to find at this future machine. So one possible example that's kind of an interesting to be considered at muon colliders in specific is leptoquarks. So these are very creatively named particles. They couple to leptons and quarks. And they can arise from sort of these low energy representations of grand unified theory. So they've existed in the literature for quite some time. And they can also show up if you have SUSY models, if you have R parity violation, then quarks couple to leptons as well. So the specific leptoquark that I'll look at, these are all bosonic particles, either spin 0 or spin 1. We'll look at a spin 1 particle called the U1, which couples, of course, to QCD color charge and the hypercharge, so it'll couple to those gauge bosons as well. But then the specific coupling structure that we have more of a handle on is how it couples to the quarks and leptons. So again, we want to sort of take the simplest example and we iterate more in the paper if you want to see details, but we'll just take this very simple example of just left-handed couplings here. So here is going to be the projection of what we could see at a muon collider. We have a couple different benchmarks for muon collider. Here is a 3 TeV benchmark that we would have. And this tells you basically the different lines up to which we think we could be sensitive. If you were to think about where the LHC would fit on this plot, it would sit at usually much lower energies, but also kind of in different coupling space. So the couplings that I'm plotting here, this is going to be the coupling of the leptoquark to the muon and to the bottom quark. The muon because we're colliding muons, and the bottom quark because it is a more recognizable experimental signature. So we're trying to make sort of the most realistic projection that we can do. If you were to look at this at the LHC, is that it would probably be coupling more strongly to the earlier generation or to B's and taus instead. So slightly different coupling space. But our reach plot here tells you again up to where we could be sensitive in this plot of this coupling to muons and B's as a function of the mass of the leptoquark. So the different lines correspond to very different physical processes happening. This Drell-Yan or Drell-Yan dagger process that's occurring is actually probing an indirect production of this new particle. So you can see an interference effect with your leptoquark and your standard Drell-Yan-ish process that will allow you to go up to much higher energies. So you're not limited strictly by the energy of the collider. You can instead, as long as you maintain precision, probe things with much higher energies. This other line that sets the leading bound is interesting because you can see it decouples from this coupling coefficient here. And that's because your leptoquark is being produced by coupling to the gauge bosons instead. So this brings us to another important physics feature of the muon collider, is that muon colliders are really also gauge boson colliders of the electroweak variety. So just like many of the important processes that we study at the LHC are really secretly gluon fusion processes, we can also study things from very high energy muons emitting lots of Z's and W's as well as photons in this process. So this would be something kind of fundamentally new, and studying the PDFs is something that theorists need to do in the next few years or decades. Okay, that was pretty quick, but I want to switch to another model now too, which is something that's a little bit more specific to a fundamental physics question we raised in the beginning, which is what is dark matter and can we probe it at colliders? So if you have a dark matter that is coupled leptophilically, which means that it mimics the structure of the eucalyptus, this is again something that's particularly well searched for at muon colliders. So I don't want to say this is the most organic realization of this model, but something that's particularly well suited for this kind of collider. So we'll take a minimal dark matter model where we have just a fermionic degree of freedom for dark matter, and we have some scalar portal. And then the scalar portal can couple in a way that's proportional to the masses. So you can think of a 2 Higgs doublet model that can give you this realization. And of course, because the leptons of the higher generations are also much more massive, then you expect the enhancement to be in the higher flavor generations, which is different sensitivity than E plus E minus or proton machines. So what we're doing to make sure that it's consistent with dark matter is we need to solve the Boltzmann equation to understand that it matches the correct relic abundance. So we're assuming a standard freeze-out model, which means we assume our model to be in thermal equilibrium early in the universe. And then as we have, as time goes on, of course, the density of these particles dilutes, and then we freeze out and the abundance of these particles is fixed. The larger couplings that we have in this 5-particle to the standard model means sort of the longer we can ride this curve down before freezing out and not annihilating anymore. So we take this model, we solve our Boltzmann equation, and we get this line in this parameter space that we call our thermal target. So this space is really a combination of some of the parameters in our model and the mass of our dark matter. So the point is that up until this line, you can be consistent with it being a model of dark matter. You might have to have additional content in your dark sector if it doesn't touch the line, but anything beyond it means that you would overclose the universe and there would be too much dark matter. So basically we're looking for sensitivity above this black curve. So the search that we would do at a muon collider is with a really standard technique that we have at colliders called Model X, where you basically look for one really well-constructed event and assume that the particle you don't see is this dark matter. So we're assuming that we're working in a regime where this particle is sufficiently massive that it almost always decays to dark matter, and we don't see it at all in our detector. And instead, we just trigger on sort of this high energy photon that would come out. So for muon colliders, we again have the additional benefit that we know completely our initial state. And so we don't know this information for proton machines because we have our PDFs that we must convolve against. So because we fully have defined the kinematics of this 2-to-2 process, is that we can do a very straightforward bump hunt because we know exactly what the energy of the photon should be if we assume a particular mass of this 5-particle. So basically we're doing a signal over background search where our background is anything with missing energy, and here it's primarily just having 2 neutrinos in our background. Okay, so we can take this search, we did it on Pythia data, and then we are able to make a bound here for what a muon collider should be. So the fact that these 2 curves overlap is basically we chose the luminosity scaling and energy such that they should overlap. But the important thing is that you see that a muon collider can really go beyond what these other lower energy experiments can do. So the strength of this machine, this energy, is really the punchline that I want to make. So if you want to
breathe then?
yeah. It is the preferred region of G-2 when we wrote this paper last year. So don't take the green band too seriously. Maybe think about it as extending to a gray band as well. But I want to point out one more curve that we did plot in this paper, which is doing a similar search, so same model, but at the E plus E minus machine instead. So one other possibility for run configurations that we talk about is a Z-pole run or the Terra Z. So we would produce something like 10 to the 12 Z bosons as an energy stage of this whole process. And then you can have things start to show up like light particles affecting the width of these decays. So we did this search basically assuming that we could hide this particle in the hadronic branching ratio of the tau decays, and that's how we set this new bound. So I won't talk too much about it. Feel free to ask me afterwards. But the point that I want to make is, again, these future machines are complementary. Even if you're searching for the exact same model, the mechanism in which that is realized can be very different. So we shouldn't be thinking about, these things as kind of repeating each other's physics program. So just to give you a couple final words about future colliders, really a lot more theoretical work is needed to understand the full scope of what these machines can do. And I think that this is something worth investing in, definitely in the next decade. And something that we need to kind of decide in the next year or two is really what are our priorities for the physics targets. So likely I think that the next machine will probably be a specifically precision machine because they are faster and cheaper to build. But I think as we're doing that, we should also absolutely be investing in the R&D for something like a muon collider, such that, again, we don't have a cliff about what we can do with future technology. And ideally, we can have multiple colliders, probably not running at the same time, but at least in different parts of the world in somewhat successive runs. So this brings me to my last point of the talk, which is sort of this intermediate of this is what we have now, this is what we'll have in the future, and sort of talking about how we can use accelerated beams from these projects to make progress in between these two periods. So I give this part of my talk this kind of generic title of auxiliary experiments. And the point is that we're using infrastructure that's not specifically constructed to do what we want to do, as we try to run parasitically or in parallel to other things to be an appendage to these big experiments and try to get a much cheaper experiment on shell to understand physics. So the point is that we should really be creative with how we utilize things that already exist to get the most bang for our buck. So there's kind of two ways that you can think about this, is you can either take data that was literally already collected and then recast it, or think about other ways that you can map this into model space. Or you can think about sort of what technologies will we need for future machines, and if those technologies are already being run, can we put a detector in front of it and get some results out of that too? So I'll talk about both of these possibilities. So the first possibility I want to think about is, again, just utilizing data that we've already collected. And one example that I had is from the mini boon microboon experiments at Fermilab. So the original purpose of these experiments is that you have this very high intensity proton beam, smashes into a target, produces a bunch of mesons, mesons decay and produce neutrinos. The neutrino oscillation is what they're trying to measure, okay? So ultimately, one of the things that they wanted to study was this neutrino scattering cross-section of the neutrinos and the nucleons that could produce a pi zero, and a pi zero goes into 2 photons, which they would see in their massive spherical detector. However, we noticed that you can have this exact same signature if instead you have this new light muon philic scalar that is too light to decay into 2 muons, and instead decays into 2 photons via a loop process. So if you assume this model, then you get basically your analysis for free, because you've already had someone understand the background very well, and you can just look if there's a bump in terms of the mass that you wanted to see. So again, we just take basically everything that they already did. We included an experimentalist to actually work on mini boon microboon to be extra responsible, and then we just recast the data. So this whole plot, we did this with data that was already collected. It was absolutely free to the collaboration, modulo Joshua's time. But we were able to achieve bounds that were better in some places and even, comparable to existing dedicated experiments just by recasting this data. So these curves that are filled in are things that we've already collected, and the curves of SBND are things that are still going to happen at Fermilab, which will extend this reach even more. So I think, we just found out about this by walking around Fermilab campus and seeing what was going on. So there has to be more of these kind of things that we can invest in to broaden our search in theory space.
Don't you have to know, like, what the oscillation, like, the parameters of the PMNS matrix are already?
So, of course. So are you asking about how we utilize the data, or are you asking about like what they're originally trying to study in mini boon microboon?
How you utilize the data.
Yeah, so I mean, kind of the biggest uncertainties that we have is in the neutrino scattering cross sections at these low energies, because you're kind of working right around the QCD like confinement scale. So there are just uncertainties in neutrino interactions that we have to worry about a little bit. So yeah, you can take all of this with maybe a grain of salt, that there are somewhat big questions about if these uncertainties can be totally trusted or not.
What was the parameter y in that plot?
Oh, sorry. So the y is just the coupling that we have. I didn't show the Lagrangian, but the idea is that the y is the coupling to this operator.
You need to assume you also have a decay to the photon, I mean, some coupling to the photons.
So we're assuming that you have an induced coupling through a muon loop. So then the other side of the story is that, let's say we're able to invest a little bit of time and money, and then what can we get out of this? Especially if the people doing the analysis aren't the people who want the infrastructure to be built in the first place. So something that I think is really important, especially for the muon community that we pay attention to, is that for the first time, we will have muon beams. Because the trickiest part of doing a muon collider is making sure that you can get a muon beam. So we have to first have a muon beam before we have a muon collider. And if we have a muon beam, there has to be something new that we can do with this, because we've truly never had access to second generation particles in this kind of intensity and precision before. So given that this is a necessary step for muon collider R&D, which has been endorsed by P5, whatever that means in today's modern age, is we should make sure that we're taking full advantage and we're ready to utilize this physics as it comes around. So again, one of the things that we should be thinking about are neutrino synergies. Muons decay to neutrinos, so wherever there's neutrinos, there's muons. And there's some ideas that we can do, again, primarily to measure these sort of neutrino scattering cross sections. But again, I want to focus more on this beyond the scanner model story, where you can take your muons and do something like a beam dump experiment. So beam dumps are really interesting auxiliary experiments because they're way cheaper than the full colliders, and they probe complementary parameter space. So the idea is that, again, you just take a beam of particles, you dump it on a material target, and then you hope that you get an interaction that can produce some new particle. The particle propagates through unaffected by other elements of the experiment, and then can decay visibly to be detected. So the idea is that all of the other standard model craft that you're producing gets swept away in the shielding region, but a weakly interacting particle can propagate through without problems. So the penalty that you pay is that if you're colliding a stationary particle with a beam, you have only access to that geometric mean of the energies, but the enhancement of Avogadro's number, because it's actually a chunk of material. So it's really going to be probing weaker couplings and lower energies than what you do at the central collider. So roughly, this is the process you should be expecting. It's like a Bremsstrahlung process most of the time. And I just want to show you sort of, again, a sweep in parameter space of these different theories for several models at various energies, assuming that we'll have some kind of staging come on for a muon collider. So one of the stages that we've talked about is a low energy stage. This number was chosen in particular that if we wanted to do like Yukawa coupling measurements of the muon, if you have mu at exactly the Higgs pole, that's less likely to happen at this point, but having a multi-GeV beam is kind of still a very big possibility. We're searching for this process. We're assuming that this particle decays visibly into 2 leptons. And of course, we have to make some choices about the geometry. So these various curves correspond to different numbers of muons on target. The 10 to the 18 is a very trivial number because we have to demonstrate that our muon bunches can support 10 to the 12 or 13 muons per bunch. So that just means that it's a year of running with these bunches, right? 10 to the 22 is probably insane, but still, maybe nice to aspire to. But we see that even again, comparing against existing beam dump experiments, is that as we go into these higher energies for these specifically flavor generation couplings, this is our leptophilic model, is that there's new parameter space to explore, even at low energies. Another possible stage of the muon collider is that they might do a low energy stage of this 3 TeV muon beam, and then each muon will have 1.5 TeV, and we consider a gauged mu minus L tau model, so the only things that are coupled to this boson will be muons, taus, and their corresponding neutrinos. So again, primary bounds are completely different at these small couplings, but moderately high energies. It's just completely empty up here. And then finally, if we have just a full energy muon collider, is that, you know, we have this big enhancement of our kinematics because things that would be short-lived enough to decay in the region that we're trying to sweep out standard model processes would be boosted enough to live to the decay region and then be observed. So then we're really able to go up and take sort of these higher coupling things that would lead to slightly too short of lived particles that other experiments are insensitive to. So even on a model as beloved and studied as the dark photon, if you have high energy muons and really just high energy charged particles, you can still make progress. And this is again at a huge discount to what the full scale collider should cost. And you might ask, okay, do we even care about this parameter space? Is there interesting physics that you can probe? And the answer is yes, is that some minimal dark matter models can still be discovered or confirmed by doing these beam dump experiments. So just to give you an idea of what that means is that if you have, again, a super straightforward extension of your standard model by just a U1 particle, a dark photon story, and then some fermionic dark matter, where now let's invert the hierarchy is that the dark matter is more massive than the mediator, is that all of these contours are still consistent with having a freeze in situation or an out of equilibrium freeze out that can be probed by beam dump experiments. So these are cheap experiments that are auxiliary to the main program that can still answer important questions like what is the particle nature of dark matter? So we should really be investing in making sure that we can get all of the physics possible out of these events. All right, so that was really what I wanted to talk about. I've shown you how we can kind of walk around in this space of new theories. Of course, I haven't been exhaustive in our physics program, but I hope that this kind of gives you an idea about how you can explore in ways that are much more generic than just choosing a singular model and going after it. So the outlook that I want to leave you with is, again, this idea that we are in an era of exploration, and that we should be thinking about how we can do model agnostic tools and strategies that can first search for hints, which we can then refine into more targeted searches, but we need to know what we're looking for before we can really take that full-bodied approach like that. And additionally, the future of colliders, this discussion is happening right now. The idea of investing in new technologies is happening right now. And we as physicists really have this responsibility to understand what machines are necessary to try to uncover the most important questions about the origins of nature. And so just to be responsible too, we should really be thinking about how we can utilize the existing or near future infrastructure to make sure that we're really going after as much of this parameter space as we possibly can. So really theory and experiments progress together, and I think now is the time to be investing in both. So thank you for your time.
Are there more questions for Cari?
Yeah.
I was just curious how much machine learning is coming into your.
So I personally don't do machine learning. I think
You
machine.
mentioned it in reference to that new
Yeah.
observables.
Yeah, so I think machine learning can be a very valuable tool. I also think that it can be a terrible black box that removes all of our physical intuition of what's going on. And how it's used is really just a question of researchers doing it. So machine learning has been amazing at improving detection techniques in particle physics for sure, just, you know, reconstructing tracks and things like that. I don't think that anomaly searches with machine learning is the way to go. But if you understand your problem well enough that the problem itself is well posed versus just find me something new, I think machine learning is very effective. But when you just send machines to find weird things, we are very often the architects of the weird things. So I don't think that that's the most lucrative path. Yeah, Edward.
Your story at the beginning about the more isotropic events.
Yeah.
Is something like that actually implemented at the LHC now?
I mean, yeah, so this strategy that I did, I was invited by the collaboration to do it on data. So we have one data set that we published, and part of it too is that I wanted to make my tools public to the experimentalists in ways that they could learn how to use. So CMS did a follow-up study actually with the event isotropy that they did without me, so they know how to use it. And they are talking about doing it in future searches as well.
I assume there's no strong signal for highly isotropic events that aren't expected.
No strong signal, no. But you know, there are deviations. So I think that these are analyses that we should repeat at higher energies to make sure that the scaling behavior is what we would expect from QCD. So at the very least, again, it's another handle to ensure that QCD is behaving how we expect it to. And I think will be important to consider, you know, as we continue to upgrade this process. No, I didn't discover new physics. I'm so sorry.
Can you say how many sigmas this agreement is?
Two. I don't know. Everything's too sigma at the LHC though.
All right, if there are no more questions, let's thank Cari again.